Hello everybody, I'm your host Hal Curtis and I'd like to welcome you to The Space Industry by SatSearch, where we share stories about the companies taking us into orbit. In this podcast, we delve into the opinions and expertise of the people behind the commercial space organizations of today who could become the household names of tomorrow. Before we get started with the episode, remember you can find out more information about the suppliers, products and innovations that are mentioned in this discussion on the global marketplace for space at satsearch.com. Hello everyone and welcome to the episode. Today we're joined by Rafael Guzman, founder and chief technology officer of SATLANTIS. SATLANTIS is a Spanish manufacturer of optical and infrared payloads for Earth observation missions and services. It is also a SatSearch membership company. Today we're going to talk a little bit about the different factors that satellite developers need to consider when choosing the right optical payload for their needs. So firstly, hello Rafael and welcome to the podcast. Is there anything you'd like to add to that introduction there?
Hello, hi, Will. No, that was a really nice introduction. And thanks very much for allowing us to be here with you today.
Yeah, let's dive in. So now, no satellite team that we've ever worked with has unlimited resources in terms of budget, mass or volume availability, or of course, appetite for risk. Compromises are always needed when picking a component, subsystem or a payload so that the overall satellite system is optimized for the application. So with that in mind, what do you think are the main aspects that need to be traded off against each other when it comes to selecting the best optical payload or camera for an Earth observation application?
Okay, so there are three large groups of considerations that a customer may want to consider when planning the best use of these satellites for their needs. The first one relates to the image quality. There are three key parameters regarding image quality to consider. The first one is spatial resolution, meaning your ability to be able to resolve details at a given scale. Typically, with the small satellites, the holy grail is to be able to resolve on the scales of 1 meter, which is the characteristic scale of the human activity. The second one is contrast. The contrast can be parameterized sometimes by the so-called MTF, or the modulation of the transfer function. But basically what it tells you is your ability to distinguish objects on the Earth's surface that will have very different flux levels, and they're very close to each other. And the third one is the so-called signal-to-noise ratio, which is your ability to see with the detail that you need, and not just the spatial resolution, but also with the amount of light that you need to recognize the object that you want to recognize. So those are the three key parameters that define image quality. Then there are another two parameters that are also good to consider as you try to extract information from those images. The second one is the so-called spectral resolution. So you need to know what kind of information you need from your object and what is the best spectral wavelength range that you need in order to analyze that information. Not only the range, but also the number of bands, how many elements in terms of the spectral information you need to extract your information. And finally is the time resolution. The beauty of the new space industry with the miniaturization of the technology is that we can launch many satellites, and that means that the revisit time can be as short as a few hours instead of the typical revisit times of a few days to a few weeks with the traditional technology. So you need to decide on what is the revisit time to extract the key information that you want from your objects in order to design the best orbits, the number of satellites in your constellation, and therefore being able to answer what you need.
Right. Excellent. So there's a number of characteristics here that are defined by both the application and the mission constraints, and obviously as well as the technology, performance levels as well. And you mentioned there that most people look primarily at a lot of people can look primarily at the spatial resolution, or at least look at it first as they're making the decision, and they're looking at what they can achieve in a certain form factor of a satellite. If the focus is only on spatial resolution, are they compromising on factors that might make image data less usable?
Yes. First, let me clarify one issue regarding the definition of a spatial resolution that is changing very quickly, particularly with the advent of the new technologies on the small satellites. So traditionally, the spatial resolution has been parameterized in terms of the so-called ground sampling distance, or GSD. That simply is the projection of the pixel of your detector through your optical system onto the Earth's surface. For many decades, this has been the paramount measure of spatial resolution. But that is the case when your optical system is limited precisely by the pixel size of your detector. But the new cameras that we are designing for the new generation of small satellites are actually diffraction limited, meaning that they are not limited by the pixel size, but they are limited by the aperture of your optics. And that has major advantages compared to the traditional approach. But that also means that you need to redefine what the spatial resolution means, because your spatial resolution in this case may not be determined by the pixel size, but by the so-called full width up maximum of the point spread function. That looks like a lot of jargon right there, but simply means that a point source will actually describe a disk on your detector when it is diffraction limited. The size of that disk very much is like the point spread function, and that eventually will be what determine your spatial resolution. That is what is called the GRD, or the ground resolution distance. Now, having said that, you may have a very, very small pixel size, but that will not be an accurate representation of your spatial resolution if you're limited by the aperture of your optics. And that's something to remember because it has introduced confusion, again, with the new space industry. Once that you have decided on the spatial resolution that you need, of course, you may have to sacrifice on the other two key parameters that define image quality, namely the contrast, or MTF, and the flux level, or the signal-to-noise ratio. Why? Because if you want an exquisite spatial resolution, the amount of light that you will receive per unit area is going to be smaller. And therefore, characteristically, you will have to sacrifice signal to noise. Also, depending again on this kind of compromise between your GRD and your GSD, you may also have to sacrifice MTF. If you want a pixel size that is as close as it gets to the disk of your point spread function, then your MTF will appear what it is called pixelated, meaning that your objects will be very much like squares. Of course, you will have a great contrast that way, but you are losing resolution. And those are the trade-offs that you have to do when deciding on the best image quality.
Oh, right. Interesting. I wonder what your views were on the sort of observation modes that are emerging and that are having an impact on how, companies might be changing or adapting their overall strategies for operating satellites and other assets in space.
Yeah, there are actually two very interesting observing modes that I think is going to introduce a revolution in the way that Earth observation is made, again, with the new space industry. Both of them basically arise from the use of the so-called focal plane arrays. So instead of the usual solution for Earth observation cameras that use the so-called push broom or drift scanning mode, in which you have just a single line of pixels that then you use to scan, like a photocopier, your surface on the Earth, you are now using an area detector. So you just don't have a single row of 5,000 pixels. You have, let's say, 5,000 rows of 5,000 pixels. And instead of just scanning, you're taking snapshot images of the surface of the Earth. Now, what that allows you to do are two things. First, it introduced a concept that we call in SATLANTIS agility. We have actually been leading this new mode of observation. In the past, you had to fix your scanning angle, your observation of your area of the Earth's surface at a fixed angle while the satellite moves in its orbit. Now, with the advent of this new technology and the various intelligent software that we're developing in companies like ours, you can take images not only when the satellite moves along its orbit, but also across its orbit. And the combination of both motions will allow you to monitor in great detail, for example, irregular linear structures on Earth. For example, coastlines, or borders, or pipelines. And these were very difficult to monitor over a very large length, let's say thousands of kilometers, when you had to maintain a fixed scanning angle. Now that you don't, then you are becoming very efficient in monitoring this type of structures. The second mode that is also very interesting is the so-called back scanning, or the hovering mode. It's like simulating the position of a helicopter that can sort of stand motionless while taking an image of a particular area on a city, for example. In this case, the satellite continues moving, but you can compensate the motion of the satellite to make sure that the pointing of your camera will be for a few seconds, not long, but typically 20 seconds, let's say, on a particular location on Earth. That allows you to derive a video with actual motion during a short period of time, but also will increase your exposure time and therefore your signal to noise. And that will also enhance your ability to see very, very fine details. And those are the two modes that are very interesting in terms of applications with the new technology.
Within those modes, or other modes that haven't been emerging, that are already in use, what sort of different types of optical sensors can be used to image within the scope of a small satellite?
Yes. So, as we say in SATLANTIS, the revolution comes at the hand of electronics. And electronics both in terms of the new sensors, as you were asking now, but also in terms of the very sophisticated and very powerful image processing techniques and image processors. Regarding the sensors, the majority of the new generation of sensors will be able to provide these focal plane arrays that I was mentioning to you. So instead of using a single line of detectors of pixels, now you will have the full area detectors. And that will go from the entire wavelength range, starting from the ultraviolet with the new generation of back illuminated CCDs, to, of course, the CMOS detectors that have already started a revolution at visible wavelengths in the new space industry. And most notably now, the new generation of focal plane arrays in the infrared. For example, the combination of the indium, gallium, arsenide detectors that can actually obtain very high quantum efficiency, a lot of signal in the wavelength range between 1 micron and 1.7 microns. But also you have the well-known technology for the focal plane arrays of mercurium cadmium telluride that will go all the way to about 3-4 microns, just already diving into the thermal infrared. And a very exciting new technology, it is the microbolometers arrays that will be able to extend this wavelength range, again, in area detectors all the way till about 20 microns. So basically covering from just a few hundred nanometers to a few tenths of microns, you have all this new generation of very high quantum efficiency detectors that will allow to do, again, things that were completely science fiction 10 years ago.
Right, so both the technology and the potential applications are being enabled across the different wavebands. Across the whole wavelength of the spectrum there. The focal plane arrays, as you mentioned, are able to be used in different bands, and the technology of the electrons is catching up. So that's really interesting, because which leads into my next question about the most prominent bands that are used and how potential customers for yourselves and other companies make that choice. So, is multispectral the most prominent band today, for example? Are RGB hyperspectral or the shortwave infrared also generating lots of interest? And are there trade-offs that companies need to consider when deciding on the right band for their application? Obviously, that's partially driven by the end user and the application that they have, but are there other things they need to consider?
That's absolutely right. I mean, as it is in human nature, we want it all. So we want a very special resolution and a lot of bands, but there are always some sacrifices that you need to do. Let's not forget that you have to operate these new technologies with a very limited amount of power, typically the same power that a light bulb here on Earth would actually use. So in terms of the multispectral versus hyperspectral capability, the first question that I would ask a customer is, what is the use? What is the application that you would like to use this multispectral or hyperspectral camera for? It is important to understand, again, what are the spectral features? Because even if you want to observe a very large wavelength range, maybe the information is in very specific wavelengths where you have these absorption or emission features that carry most of the information. So you may not need the entire observation of the wavelength range or the entire spectrum, but rather to select your bands on the specific wavelengths that carry most of the information regarding what you want to observe. It's not the same if you want to observe, again, the vegetation for high precision agriculture, or if you want to observe methane emission in the atmosphere. It will be very specific, the wavelengths that you will want to do for the second one compared to the much more general approach in the first one. So first of all let's clarify the application to try to optimize the selection of the bands, because the more bands that you need, therefore you will have to sacrifice signal to noise per band. And again, that will also limit how faint will be the objects that you can actually observe in all the bands. So that will be very much the trade-off that the customer will need to do.
Interesting. So it sounds like the procurement of any camera is quite an involved process with lots of steps where you're finding out about the customer and they about you. That mirrors the practices you see in a lot of the procurement for space technologies. So in those long discussions, or even if they're short discussions, there's presumably lots of areas where customers might make mistakes or have misconceptions about what is possible and what they need to be doing. So I wondered what sort of common misconceptions you might see on the buyer side when it comes to selecting optical payloads.
Yes, so it's very, very similar to when you go to a store and you want to buy the latest electronics. And of course, you just go there and you try to get the latest model with the latest perks and absolutely with fully loaded. Then you realize that perhaps you are paying for things that you don't need and that you will use very little. And it's something similar over here. So that's why we try to engage with the customer and to try to understand their needs. That is the key thing. And we always recommend different options that will optimize the outcome of the choices for cameras and satellites and orbits depending on their application. And I think it's very important because I think that we all have this natural trend that more is better, but that is not necessarily so. And if you're going to select a general technology, it may not be optimized for the specific application that should be your top priority. And as a result, it may not be as competitive. It may be more general, but it may not respond optimally to the requirement or the application that the customer actually needs. And that very much is the very first step in the relationship with the customer.
Do you have any other advice for potential buyers looking to select an optical payload, particularly if it's their first purchase?
It's very much related to the previous answer. So it is to help the customer if the customer already does not have a clear understanding of the requirements for their applications. It also means that we want to be fully involved in understanding the application that the customer would like to use our technology for, so that, again, we can optimize it for the requirements defined for that particular application. So the dialogue, the trust, the understanding between technology and uses is very important to make sure that the customer will get the best solution for their money and that they will be completely satisfied.
Well, it sounds like a great approach. And I think you've already maybe answered most of this, but I wondered if there was that you could share with us about the process that SATLANTIS goes through to help a customer choose the right system for their needs.
Basically, how we have done it with a couple of customers that we have had so far in the oil and gas industry. For example, about a year ago, or a year and a half ago, we were approached by a Texas oil and gas company, and they wanted to monitor the oil pad activity over a very large oil field, a few thousand square kilometers. And they wanted to do this every day. So we learned exactly what was the type of activity that they wanted to monitor. And by understanding that type of activity, we were able to translate that into the actual requirements on the image quality and the orbit characteristics. in terms of the spatial resolution, in terms of the contrast and the signal to noise ratio. Then what we did is to do very realistic and accurate simulations of areas that would look very, very similar to those oil fields for different cases, so that we were able to illustrate how we could optimize one parameter versus other in terms of the applications that the customer required. We were able to share these simulations with them. They were able to see actual images taken with a different satellite that then we used to simulate our performance of our camera and our satellite and our orbits for the customer to decide. And as a result, we reached a perfect agreement on what would be the best choice of the technology. A similar case, for example, I can mention now for a completely different application, which is the detection of atmospheric methane, also associated to leaks from the oil and gas industry. In this case, because this project is definitely much more engaging and more complex, if we want to reach the very low detection threshold that this gas company requires, what we have done is actually to work together. So again, we started with the initial simulations after understanding the problem, but then we are developing the technology and we want to calibrate that technology, always going hand in hand with this gas company. So we will go to their facilities and we will be able to start testing our technology from the ground at the same time that we use their own traditional approach to detecting the methane leaks from these type of facilities. So that would allow us to immediately parameterize what will be the level of detection that we can reach with our technology, but also to calibrate that technology because they will be able to have not just an image, but an actual flux in terms of kilograms per hour or tons per year, which is what they require in order to understand globally for all their facilities what is the extent of the problem and, of course, being able to fix it. That will be the first step. Then we'll take the technology that has been fully calibrated and tested from the ground on board an airplane, and we will do exactly the same thing and in real time being able to take measurements from the air and from the ground with their technology and introduce a second level of complexity because now we have to take into account the full effect of the atmosphere. But we have the ground truth from their own sensors and we have our own fully calibrated technology. And now we can focus on how to correct for the atmospheric effects. And finally, after we have done this, then we will be able to launch the constellation that this customer needs in order to monitor every 2 weeks all their facilities nationwide. By then, they have the complete trust, the complete confidence that the numbers that we are deriving are fully calibrated in the units that they are used to from the ground, and they can use it directly. I want to emphasize these two examples as the way in which we work in SATLANTIS. We're not in the business of a general usage. We don't launch the satellites and then we find customers. No, we actually talk to the customers, we work with the customers, and we design the best technology and the best mission analysis that will meet the customer needs.
Great. It sounds a fascinating process, and that you have such opportunities to iron out lots of the details that might otherwise be faced with. Calibrating the systems on the ground, and then by airplane, you'll presumably dealing with aspects of data quality and interfaces between systems and all that sort of thing. And it's really interesting to learn how much goes into something that there's such a complex system and a process, but that simplifies down to the one or two numbers that your clients need, over a period of time. So related to that is one of my last questions here is, I wondered whether you saw more and more intelligence being added into the Earth observation missions and application areas through the use of AI on satellites. I mean, we've heard of examples that have either been tested or have been designed for things like ensuring that satellites only images certain features when they're detected, or only images areas without cloud cover, for example. I wonder what you thought about that area.
Yes. You have touched upon a huge area of growth. No, this is absolutely essential. First, because technology allows you to do this with the latest training algorithms for artificial intelligence and also for machine learning, but also because of the huge amount of data that the new constellations of small satellites will be able to provide. So, just to give you an idea, a typical mission of a few tens of satellites over 3-4 years will generate petabytes of data, as much information of the entire internet. So you really need to generate these type of tools. Also, you need to generate these type of tools as a clear example with the case that you just mentioned. So not every time that you are taking images from the Earth's surface, you are actually obtaining an image that you can use to extract information from. For example, if you have fully cloud cover over the entire field of view. So the sooner that you can learn that this image is unusable, is much better, because then you don't use your limited resources to be able to acquire, process, and transmit the data back to Earth. You just focus on on those images that really carry information. That's one aspect. But the second aspect is that remember that every 90 minutes we are just going once around the Earth, taking images. Eventually, you're going to have multitude images of the same location on Earth. If you want information instead of the image, the information will be in the dynamic aspect of that Earth observation, meaning in those pixels that actually change. The pixels that don't change, you already have the information from previous passes, right? So you need to start introducing these AI algorithms to identify the pixels that change. But the pixels that change for the real reasons, because of the change is associated to the phenomenon that you want to study. It's not because there were clouds in one and no clouds in the other. It is not because there were shadows in one pass and no shadows on the other, because of the change of the solar time. So that is, again, a great area of growth for artificial intelligence. But once that you see where the pixels that carry the information are, you go into a second step, which is to extract the information using machine learning algorithms. So, and that's why you will be able to see, well, I want to see a boat, that it is in a particular location, and how I can distinguish a boat from a different floating artifact in the ocean. And that's, again, another huge area of growth. So it's very important because, as we said, you're going to be generating petabytes of data, and in reality, you just only want to focus on those pixels that carry the information.
Yeah, well, you just mentioned AI and the use of more intelligence and more data. You've mentioned things like the use of focal plane arrays and this ability to control the imaging angle and those sorts of emerging modes of operation for small satellite optical payloads. I wonder what other advancements, particularly in Earth observation technologies, you're particularly excited by or interested in, or that you're predicting might occur in the next 3 to 5 years.
Yes, well, as you can see, Howell, I'm really excited about this new industry. I think we're the new dawn of a new revolution in terms of access to space and the information that will be available to every citizen on Earth from space. But if I have to choose one particular technology that is already being designed and developed that may help to change, to provide the next quantum leap in the advancement of the new space industry, is the so-called flight formation. So miniaturization is great. It's great and it's amazing what you can do thanks to the electronics, but also the new materials with very small satellites. But we're still very much limited in terms of power and even limited in terms of resolution. At the end of the day, physics will tell you that the very best resolution that you can achieve will be related to your size of your optics. And it's going to be very difficult to compete with very large satellites that obviously can have much, much larger optics. Of course, at the 2 orders of magnitude, the cost. Now, if instead of having a single satellite, you can have several satellites but not in a constellation, actually in a cluster formation, meaning that you have now several small satellites that will act as one. And that is the beauty, because they will be able to maintain geometric configuration that either due to a combination of payloads in different wavelengths or the use of different techniques like interferometry will be able to compete now the whole cluster with a single, much more expensive monolithic traditional satellite, and not only in terms of performance, but also in versatility, in the number of sensors and in the changes of the configuration that will be able to offer more and more services. And I think that within a few years, I think 3 to 5 years, we will start looking at these clusters of small satellites with a performance that I think that we cannot even dream of right now.
Well, fantastic. That's a fascinating application there. And I think that's a great place to wrap up the discussion, Rafael. I really appreciate the information you've shared with us today. I think our listeners are now much better placed to understand how to select the best optical payload for their own Earth observation missions and needs. And with the examples you've shared and the advances in the technology that you explained to us today, I think that the companies that might benefit from using space in different ways have hopefully got some really great insights into what Earth observation could offer them. So thank you very much for being with us today, Rafael.
Thank you, Howell. And also on behalf of the entire team here at Atlantis, I want to thank you and everyone in this business actually for contributing to this very exciting time of this new revolution provided by the new space industry. So thank you very much and good luck to all.
Oh, that's great. We really appreciate it. And to all our listeners, remember that you can find out more about Satlantis at satsearch.com. On the platform, we've got technical details of various different space products and services from around the world, along with documents like datasheets and CAD models. And you can also make free requests for quotes, introductions to businesses, or whatever other engineering or procurement needs you might have. Thank you for listening to this episode of The Space Industry by SatSearch. I hope you enjoyed today's story about one of the companies taking us into orbit. We'll be back soon with more in-depth, behind-the-scenes insights from private space businesses. In the meantime, you can go to satsearch.com for more information on the space industry today, or find us on social media if you have any questions or comments. To stay up to date, please subscribe to our weekly newsletter, and you can also get each podcast on demand on iTunes, Spotify, the Google Play Store, or whichever podcast service you typically use.